Hello students, today we are discussing the topic moving coil galvanometer. When in third chapter we are talking about the current and the voltage or potential difference, then what are the instruments which are used for measuring a current? Ammeter. Ammeter is a device which is used for measuring current. In the same way, voltmeter is a device which is used to measure a potential difference. And in third chapter, in meter bridge and in potentiometer, we have used a device which gives a null deflection. Yes, and that is a galvanometer. So here you will understand that we can use ammeter, voltmeter in such a way that the galvanometer is included in it. So by using galvanometer, we can prepare ammeter, voltmeter, and galvanometer is also used to detect the current in the circuit. To detect the current in the circuit, that means if the current is there in the circuit, it will show deflection. And if current is not there in the circuit, it shows the null deflection. And that is the reason we have used it in potentiometer and meter bridge. So what is the principle of this moving coil galvanometer? The principle of moving coil galvanometer is when a current carrying coil is kept in magnetic field, torque acts on it. This you are knowing, students. When a current carrying coil is placed in a magnetic field, then torque acts on it. So what is the construction of this moving coil galvanometer? In moving coil galvanometer, we are having a rectangular coil which is wrapped on a soft iron core, and it is placed between the pole pieces of the permanent magnet. The rectangular coil is free to rotate about its axis. And at the other end of the coil, we are having a pointer which shows the reading on the scale, and here below the coil, it is connected with a spring. This is a spring, and this spring will produce a counter torque, so that the coil which get rotated, it get balanced at a one point. That we are going to see in the working. So what is the construction? Here we are having a rectangular coil. These three lines are of the coil, which is wrapped over a soft iron cylinder, and it is placed between the magnets such that they will produce a radial magnetic field. The soft iron cylinder, it is used for the purpose that it will increase the strength of magnetic field, and it makes this magnetic field radial. Uniform radial magnetic field is experienced by the coil. And pointer is attached at one end of the coil, which shows the reading on the scale. Now, what is the working of this moving coil galvanometer? As you know, students, when a current carrying coil is kept in a magnetic field. Now, we are giving the current to the coil, so it will become a current carrying coil, and which is kept in the magnetic field, which is kept in a magnetic field. Then what will happen? According to our Fleming's left hand rule, when we are having a current magnetic field, then force will act on it, and the force is such that it will produce a torque. And we have seen the expression for torque, which is equal to IA cross B. Here the field is radial, so theta is 90 degree. So sin theta, it is become equal to 1. Sin theta equal to 1. For n number of turns of the coil, the expression for torque, we can write NIAB. For n turns, the torque will become NIAB. As we have seen, the torque which is produced in a coil, it is equal to NIAB. Now, In the construction diagram, we have seen that the rectangular coil, the end of the rectangular coil at the base, it is connected to the spring. And that spring, it also produces torque. But the torque which is produced by the spring, it is called as a counter torque. What is a counter torque? Counter torque means a torque which is in opposite direction to the torque of the rectangular coil. So what will happen due to that counter torque? This counter torque which is provided by the spring balances the magnetic torque. Balances the magnetic torque and produces a steady deflection phi. Here our torque in the coil, torque of coil, it will be same as the counter torque produced by spring in equilibrium condition. In equilibrium. So in equilibrium, the torque of the coil, it is NIEB, and the counter torque which is produced by the spring, it is equal to K phi. Here K is a constant and which is called as a restoring torque per unit twist. Twist which occurs in the spring. Restoring torque per unit twist. So here we can write the expression for phi, that is deflection which is produced by the coil. It is NIAB upon K. So if we arrange it, phi will become equal to NAB upon K into I. Here you will see that the term NAB upon K is a constant term. N, number of turns of the coil, A, area of the coil, B, the magnetic field in which the coil is kept, and K, it is called restoring torque per unit twist. And for a given spring, this K is constant. For a given coil, for a given arrangement, NAB upon K will be a constant. So we got deflection which is produced by the coil, or deflection which is produced by the galvanometer pointer, it is proportional to current. It is proportional to current which is flowing through the coil. So for this, by using this principle, the galvanometer is used to detect the current. As you have seen in a meter bridge or in a potentiometer, as soon as there is no current, galvanometer will show null deflection. So galvanometer is used to detect a small current also. Galvanometer is used as an ammeter and galvanometer is used as a voltmeter. Based on this, phi is proportional to I. Now let us see how the galvanometer is used as an ammeter. Galvanometer as an ammeter. Can we keep a galvanometer in the circuit at the place of ammeter to measure the current? No. We cannot use galvanometer as such like a ammeter. There are two reasons why we are not using galvanometer as a ammeter as it is. So what are the two reasons? The galvanometer is a very sensitive device. It is very sensitive device and it gives full scale deflection for the small amount of current also. Galvanometer as an ammeter. As ammeter. We cannot use as such. The two reasons are there. What are the two reasons? The first reason, galvanometer is a very sensitive device. Galvanometer is a very sensitive device. It gives full scale deflection for very small current in microamperes also. Microampere also. And the second reason is that a galvanometer is having very large resistance. The galvanometer resistance is very large. And as you know, ammeter always we connect in series for the current measurement. So when you will put the galvanometer with very large resistance in series with the circuit, what will happen? The amount of current which is flowing in the circuit will change. And the reading which is given by that will not be the correct reading of the current. It will show the change in the reading of the current other than the current which is flowing in the circuit. So that is the reason galvanometer we cannot use as such as an ammeter. As it is a very sensitive device, it gives full scale deflection for microampere current also. And second thing, the resistance of galvanometer is too much, so it will not show the same value of the current. So what we have to do for this, that we will see. Now we are going to discuss the important topic galvanometer as an ammeter. How the galvanometer can be used as an ammeter. As we have seen, galvanometer cannot be used as such as an ammeter because the resistance of galvanometer is too high and it affects the current measurement of the circuit. So what we have to do? For this, we have to take a galvanometer whose resistance is given by Rg, and we have to connect a small value of shunt resistance in parallel to it. Small value of shunt resistance Rs in parallel to it. The whole circuit, the whole arrangement like this, it will act as an ammeter. Now this is our ammeter. What is ammeter? In ammeter we are having a galvanometer resistance in parallel with a small shunt resistance. So what will happen when we are connecting a small shunt resistance in parallel? Here we will see what is R equivalent. R equivalent for this arrangement, it will become 1 upon Rg plus 1 upon Rs. So R equivalent equal to Rg Rs upon Rg plus Rs. Now you can see, though the galvanometer resistance is too high, the R equivalent become less than Rs. R equivalent become less than Rs. And due to this arrangement, the current measurement will not get affected. Current measurement of the circuit will not get affected and it will act as an ammeter. So, ammeter is also called as low resistance galvanometer. Ammeter, it is also called as low resistance galvanometer, and ideal ammeter is having zero resistance. Ideal ammeter is having zero resistance. This is the reason. That's why the ideal ammeter is having zero resistance. Now we want to see what is current sensitivity of this ammeter, or you can say converted ammeter. Phi upon I, it is called as a current sensitivity. And we know from above equation which we have calculated earlier, phi is NABI upon K. So phi upon I is NAB upon K. Current sensitivity is also called as deflection per unit current. If we want to increase current sensitivity, we have to increase number of turns of the coil and current sensitivity will increase. Increase in current sensitivity means for small current also the galvanometer should show deflection. So that is called as a current sensitivity. Now let us discuss as a galvanometer as a voltmeter. That means with the help of galvanometer we are making a voltmeter. As you know, voltmeter is used to find out potential difference between any two points in a circuit. That means if we are having a circuit like this, I have written a circuit and we are connecting a voltmeter in parallel to it for the voltage measurement across any two points in the circuit. Now at the place of voltmeter, suppose I am keeping a galvanometer. Will it act as a voltmeter? No, it will not act as a voltmeter. Why? What is the reason? The reason is that the galvanometer is having very high resistance. The galvanometer is having very high resistance and it is connected in parallel with it. It will draw current through it, and so the potential difference measurement of that circuit or between the two points will not be correct. According to the standard, the measuring device should not create a disturbance more than 1%. It should be always less than 1%. So how the galvanometer can be converted as a voltmeter? How we can use a galvanometer to convert it into a voltmeter? So take our galvanometer. This is our galvanometer. Its resistance I am writing as Rg, and we are connecting one more large resistance R in parallel with it. And now this arrangement, it will act as a voltmeter. This arrangement, it will act as a voltmeter. So what is the R equivalent of this? R equivalent is Rg plus R. Rg plus R. And now this we can use as a voltmeter. How we can use this as a voltmeter? Since the resistance equivalent is greater, so the amount of current drawn by the voltmeter, this voltmeter, is less. So the potential difference measurement of the circuit or between any 2 points will be correct. It will not disturb the value of the potential difference between any 2 points. So we are connecting a resistance R in series with a galvanometer to convert it into voltmeter. Now suppose I want to convert the galvanometer into the voltmeter of range V. Voltmeter of range V. Here I want to find out how much resistance I have to connect in series. How much resistance I have to connect in series such that it will get converted into voltmeter of desired range V. Let us consider that the current which is going through this galvanometer is Ig. Current going through this galvanometer is Ig. So by using Ohm's law, Ig equal to V upon Rg plus R. V upon Rg plus R. So Rg plus R, Rg means resistance of galvanometer, is V upon Ig. So R will become V upon Ig minus Rg. So this is the desired amount of resistance which I have to connect in series with given galvanometer to convert it into a voltmeter of desired range of voltage V. Desired range of voltage V. So ideal voltmeter is having infinite resistance. Ideal voltmeter is having infinite resistance. Or you can say a voltmeter is a galvanometer with very large value of resistance. As we have seen earlier about the current sensitivity, here we are going to discuss about voltage sensitivity. We are having earlier the equation for phi. Phi equal to NAB upon K into I. Voltage sensitivity is phi upon V, and phi upon V equal to NAB upon K into I upon V. And I upon V, we can write it here. We are having I upon V. This I upon V we can write as 1 by R. I upon V we can write as 1 by R. So it will become NAB upon K into 1 upon R. That is called as voltage sensitivity of this voltmeter. Now we are discussing the important question which is asked many times. Increasing current sensitivity may not necessarily increase the voltage sensitivity. Why? May not necessarily increase the voltage sensitivity. Why? This is the question. Now current sensitivity, as we have seen, the equation is phi upon I equal to NAB upon K. If we want to increase current sensitivity, we can increase the number of turns of the coil. So let us increase the number of turns of the coil. N turns, let us make it double 2N. So phi upon I will become 2NAB upon K. 2 times NAB upon K. So phi upon I, it will become 2 times phi upon I. The new phi upon I, it will become 2 times the initial current sensitivity. Now let us see what will happen to the voltage sensitivity by increasing the number of turns. So voltage sensitivity, as we have written the equation earlier, phi upon V equal to NAB upon K into 1 by R. NAB upon K into 1 by R. N, number of turns, you increase to 2N. As the number of turns increases, the length of wire increases. Length of wire increases, that means resistance also increases. R is proportional to length. So, R will become 2R. R will become 2R. So, what is the change in voltage sensitivity? The phi upon V will become 2NAB upon K into 1 upon 2R. 1 upon 2R. These two will cancel out. These two will cancel out. So, new voltage sensitivity after increasing the number of turns, that is phi upon V, new. It is same as the original voltage sensitivity. It is same as original voltage sensitivity. And thus we can see that if we increase the number of turns or if we increase the current sensitivity, it does not mean that there is increase in voltage sensitivity also. Now we are discussing example 4.12 of the NCERT book. In the NCERT book, they have given this circuit diagram in which we are having a battery of 3 volt, resistance of 3 ohm and an ammeter is connected there. The question is find out the value of current. Find out the value of current if in the first case it is at the place of ammeter we are having a galvanometer with resistance 60 ohm. Ammeter is replaced by a galvanometer having its resistance 60 ohm. So let us see, our circuit diagram will become like this. This is a 60 ohm galvanometer which is kept at the place of ammeter. We are having 3 ohm resistance in series with it and a battery of 3 volt. Now as you know, the total resistance R equivalent of this circuit will be 63 ohm. We want to find out the amount of current. I equal to V upon R equivalent. And V of this circuit is 3 divided by 63. So here we are getting the value 0.048 ampere. 0.048 ampere. Now in the second case, here we are having a galvanometer of 60 ohm at the place of ammeter and a shunt resistance of 0.02 ohm is connected in parallel with it. So let us draw our circuit diagram. Here we are having at the place of ammeter, we are having a resistance 60 ohm and a shunt resistance of 0.02 ohm is connected. This is Rg and this is Rs. This is our ammeter. And then it is connected with 3 ohm here and connected with a battery of 3 volt. This is our ammeter A. Now what will happen? First we have to calculate the parallel resistance of these two. So 1 upon R equivalent equal to 1 upon Rg plus 1 upon Rs. So 1 upon Rg plus 1 upon Rs. You can write R equivalent equal to Rg Rs upon Rg plus Rs. And here when you substitute Rg is 60, Rs is 0.02, again Rg is 60 and 0.0. That is R equivalent. The value of R equivalent we are getting 0.02 ohm. And what is the total resistance of circuit? Total resistance of the circuit will become 3 plus 0.02. So it will be 3.02 ohm. It will be 3.02 ohm. Now we want to calculate the current. So I equal to V upon R. V is here 3 divided by 3.02 and we are getting the current 0.99 ampere. That is our second case. This we are discussing second one. Now let us consider the third case. This ammeter is replaced by ideal ammeter, and as you know, the ideal ammeter is having a resistance 0, R equal to 0. For ideal ammeter, R equal to 0. So R equal to 0, so total resistance is R only. Total resistance of the circuit is 3 ohm only. Now we will find out the current. Current equal to V by I. So 3 upon 3 we are getting 1. 3 upon 3 we are getting 1 ampere. Now from this example also, students, you can find out that a galvanometer we cannot keep at the place of ammeter as it is. If you are keeping galvanometer at the place of ammeter as it is, see the amount of current which we are getting. Too much difference is there in the amount of current. And now if we are putting a small shunt resistance in parallel with the galvanometer, then you see the amount of current which we are getting in the circuit. And for ideal ammeter also you see it is 1 ampere. 1 ampere and 0.99 ampere, they are much closer to each other. So we can say the ammeter we can prepare by using a galvanometer. How we can use galvanometer as an ammeter? By putting a small shunt resistance in parallel with it.